Have you ever wondered how your smartphone works, or how your car knows when to brake? The answer is semiconductor chips. These tiny chips are the brains behind almost all modern electronics. Semiconductor chips, also known as integrated circuits, are like miniature cities of electronic components. They are found in everything from smartphones and laptops to cars, airplanes, and even refrigerators. Without semiconductor chips, our world would be a very different place. We wouldn't have the internet, smartphones, or many of the other technologies we rely on every day. These chips are incredibly complex and require a sophisticated manufacturing process to create. The journey of a semiconductor chip begins with a surprisingly common material, sand, but not just any sand will do. We need silica sand, which is extremely pure silicon dioxide. This special sand undergoes a series of refining processes to extract almost perfectly pure silicon. Think of it like sifting the sand until only the tiniest, most perfect grains remain. This purified silicon forms the base for our semiconductor chips. It's called a semiconductor because it can conduct electricity under certain conditions, making it ideal for creating the tiny switches and transistors that make up a chip. But silicon alone isn't enough. We need to add other materials called dopants to give it the properties we need to build complex circuits. Once we have our ultra-pure silicon, it's melted down into a giant molten blob. This blob is then carefully cooled and grown into a cylindrical ingot, kind of like a giant silicon sausage. This ingot is then sliced into thin, round wafers. These wafers are incredibly thin, often less than a millimeter thick, and extremely fragile. They are also polished to a mirror-like finish so that circuits can be printed on them with incredible precision. These wafers are the foundation upon which our chips will be built. Each wafer can hold hundreds or even thousands of individual chips. Now the real magic begins. Using a process called photolithography, we project intricate circuit designs onto the silicon wafer. It's like creating a miniature city map, layer by layer. Imagine using a tiny stencil and light to create the roads, buildings, and infrastructure of a city. That's essentially what we do with photolithography. We use a special light-sensitive material called photoresist that hardens when exposed to ultraviolet light. By shining UV light through a patterned mask, we can transfer the circuit design onto the photoresist. The masks used in photolithography are incredibly precise. They contain the blueprints for the chip circuits and are made with extremely fine detail. Think of them like the negatives used in old-fashioned photography, but much, much smaller. The UV light used in this process is also very specialized. It has a very short wavelength, allowing us to create extremely small and precise features on the wafer. This process of exposing the photoresist, developing it and etching away the exposed areas is repeated multiple times, layer upon layer, to create the complex three-dimensional structure of the chip. Remember those dopants we talked about earlier? Now it's their time to shine. Doping is the process of adding impurities to the silicon wafer in specific areas to change its electrical properties. By introducing elements like boron or phosphorus, we can create areas that are either positively or negatively charged. These charged areas allow us to control the flow of electricity within the chip, forming the transistors that act as the on-off switches of the digital world. It's like adding special ingredients to our silicon recipe, giving it the superpowers it needs to perform complex calculations and store information. As we add more layers, our chip starts to resemble a miniature three-dimensional city. Each layer has a specific function, like connecting different components, insulating circuits, or providing power. Imagine building a city with skyscrapers, bridges, and underground tunnels. That's what we're doing on a microscopic scale with each layer we add to the chip. This intricate layering is what allows us to pack billions of transistors onto a chip the size of a fingernail. Once all the layers are complete, it's time to test the chips to make sure they work properly. This is done using automated testing equipment that checks the functionality of each chip on the wafer. After testing, the wafer is cut into individual chips, each one a tiny marvel of engineering. These chips are then packaged in protective casings that provide electrical connections and help dissipate heat. The packaged chips are then ready to be shipped to electronics manufacturers around the world, where they will be assembled into the devices we use every day. The semiconductor industry is constantly evolving, with engineers and scientists pushing the boundaries of what's possible. As technology advances, we are able to create even smaller, faster, and more powerful chips. These advancements are driving innovation in artificial intelligence, machine learning, and other cutting-edge fields. The future of technology is closely tied to the future of semiconductor chips, and the possibilities are truly limitless.